Hey, AP Chemisters, this is Mrs. Vanderlei bringing you Blankwalle, Chapter 6, Part 6. This is a really important section. They all are, I know. But this one is introducing you to enthalpy. Enthalpy is probably what you're going to be seeing a lot more of on the AP versus a delta E kind of a question, okay? So enthalpy is the heat evolved in a chemical reaction at what? Constant pressure. Oh, what was 6.5 all about? Constant volume. But this is constant pressure. So let's check this out. Oh, by the way, the H here that you see for enthalpy really originates from the idea of heat. All right, so that's why they call it delta H, because it's a heat value. And so delta H is the sum, which I'm going to add, of the internal energy plus the product of pressure times volume. Okay, so here it is. So the delta H is equal to delta E plus P delta V. Well, look what happens. You have your Q at delta P plus W, and then what delta E is? Plus P delta V. And what happens to my work? They cancel out. So I'm left with delta H is equal to Q at constant pressure. And this is another kind of a unit where you really have to look at your units, okay? What do you want delta H in, kilojoules or kilojoules per mole? And that is something you need to keep your eye on, keep your focused on, and answer the right question, okay? Folks, delta H is going to be a lot like Q, so the similar kind of questions I ask you about Q will work the same as delta H, okay? So we have the sign of delta H. Okay, heat flows into the system from the surroundings. It's endothermic. Why? Because you start at the bottom, you gain energy, and you finish up here, okay? So how would I write that as a reaction? This is, if you can look at the fine print in here, you're talking about 1 mole of nitrogen gas and 1 mole of oxygen gas making 2 moles of nitrogen monoxide. So if you are gaining energy, if it's endothermic, you put your heat on your reactant side of the arrow. Okay, very important. So look at that. Delta H is positive. Why? Because final minus initial is a positive number. Okay, so final minus initial is a positive number. So it says, explain how a cold pack works. You've already seen this, really. A cold pack has 2 pouches in it. One of them has water and one has typically ammonium nitrate or a similar compound, but ammonium nitrate is very common. And so when you punch the bag, you break those 2 inner bags open so the water is allowed to mix in with ammonium nitrate. What happens is that you're breaking the attractions between the ammonium and the nitrate. And so what happens here is that the water is supplying energy to the ammonium nitrate to dissolve. The energy that is being released as it dissolves is not as much as the amount of energy required to get that process going. So your net result, it needs more energy than it releases, and that's why it's an endothermic reaction. So it's gaining the energy from the water cools down, and then you can take advantage of that if you need a cold pack. Okay, let's go on the next page. So this is the opposite, all right? Heat flows from the system to the surroundings is exothermic, and here is our example here. Notice we start with methane and oxygen. This is my start. So here are my labels. I forgot to stick them in there. So here we have, so the start of the reaction is at the top, you finished at the bottom. So when you subtract, what happens? Final minus initial is a negative number. That means it's exothermic. So where do you put your energy? Over here in the products? That means that the energy is flowing from the reactants to the products, and then you release some heat, okay? So it says here delta H is negative. Look at the picture and explain why. I think I just told you why. Because you finish at a lower spot than you start, so when you subtract, you get a negative number. So how does burning natural gas work? Well, this reaction, okay, is exothermic. It's producing heat, and then the surroundings is absorbing the heat. So what are the surroundings? Air, maybe you, maybe a pot of water if you're trying to heat up some water. So that reaction ends up at a lower energy level than it started. So where did the energy go? It went to its surroundings. It went to the heat. Okay, so hopefully that makes sense, and hopefully you'll be able to ask the same thing yourself. So there are some questions here. Why don't you pause this, answer endo-exo, sign of delta H. Again, this is review from Q, so hopefully that this is not too difficult. So pause, see what you get, come back. So sweat evaporating from skin, delta H will be positive because it is gaining energy from your skin to become a gas, to evaporate. So your delta H is positive, it's endothermic. Wood burning in a fire, it's releasing energy to the surroundings. Delta H is negative, it's exothermic. Rubbing alcohol quickly, evaporating on your skin, it's the same as letter A. How does the liquid become a gas? It gains energy from your skin, so they become a gas. Gasoline burning in the engine, delta H is negative, it's exothermic, therefore there's energy to move the piston and yada, 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 so it is exothermic, okay? All right, so problem number 25, looking at this picture, you are to label each process as endo or exo. And actually this visual is really, really important. We're gonna come back and look at this in later chapters and revisit this whole idea. So if you're going up, if you're going from a solid to a liquid, it has to gain energy, therefore it can move better. If you go from a liquid to a gas, it has to gain energy so it can separate from its buds there, okay? So if you're going up this process, it's endothermic. The reverse is exothermic. So going from a gas to a liquid or a liquid to a solid, you all have negative delta H's. And we're going to be using these idea of vaporization and fusion again in this later chapter. So we'll probably come back and revisit this picture again when we hit that section. So again, energy, I don't know why I care, is defined as the ability to work and produce heat. So, probably for number 26, determine the signs of the heat and work for the two systems. Again, very, very similar to what we've already done. So why don't you go ahead and fill this out down below and come right back. Okay, so one more time, if you are leaving the system, it's negative. If it's going into the system, they're positive. So I think problem number 27 is in the wrong place. I think this belongs in an earlier section. So this is actually a pretty good review. Why don't you go ahead and do this, make sure your signs are correct. So pause this, come back when you're done. All right, so here is what I got. It's endothermic, so Q is positive. Heat is flowing from the system to, or excuse me, the surroundings into the system. And what else is happening? Work is done on the system, so it's like pushing the syringe in with your hand, so it's also positive, and you get a positive 17 kilojoules. The next page is going to give us more current material, going back to the enthalpy again, so, and more calculations. I'll see you in a second. All right, so this is an important idea here, exo and endothermic process, a molecular view. So if an exothermic reaction gives off heat, where does that heat come from? You've probably heard me say this before, it comes from the bonds, okay? The internal energy is the sum of kinetic and potential. The potential is the source of the exothermic chemical reaction. The potential energy, star this, underline this, comes from the attraction between the protons in the nucleus and the electrons. When a chemical reaction occurs, the bonds are broken and new bonds are made. If the reaction is exothermic, then the organization of the protons and electrons are at a lower potential energy than before. In other words, it's more energetically favorable. So look at this diagram over here. If you can't see it, there's a PE here for potential energy, okay? So let's kind of recreate this, okay? If the reaction is exothermic, then the organization of the protons and electrons are at a lower potential energy than before. So if I start up here, this is where I begin, okay? Look, I'm going to increase the energy momentarily. Why? Because I'm breaking bonds. Breaking bonds always requires energy. But then when the new bonds are being formed, look at that. I end up at a lower place than where I started. So this would be an energy diagram that you're going to see over and over again. You always start going up. But if it's exothermic, you end up lower than before. So write this down. This is exothermic. Will you draw another graph for me? Because I want to look at an endothermic real quick. So what do you think an endothermic reaction is going to be? Endothermic is the opposite. So how would this read here? If the reaction is endothermic, then the organization of the protons and electrons are at a higher potential energy than before. So again, look at this. We're going to break bonds, and then we're going to gain energy, and then new bonds are formed and you're released. But look at the difference here. It took more energy to break these bonds. Why? Because of this attraction between your protons and your neutrons than what you had before. Endothermic isn't very common, is it? We're going to look at that idea in chapter 18, which actually follows chapter 6. So if it's not very common, what does that mean? Does this reaction typically go? Not a lot of them do. Some do, most don't. Okay, so this is an endothermic. Could you write that down? This is an endothermic graph. I didn't have a place to do that. All right, so stoichiometry. Oh, look at this. There's a star here. Do you remember what happened last time we had a star in our notes? Yeah, you saw it later, didn't you? So this is a really important section. I think it is so important that I'm going to stop here and look for part 2, and we'll begin with stoichiometry. So don't wait to be great. See you next time. Bye-bye.